right, so how would that work in a problem? Well, here we are told that we have a logarithmic function, and we're given a couple of data points. F of 3 equals 7, and f of x, or f of 6, equals 10. So without finding the particular equation, can I find f of 12 and f of 24? Well, if I set up a table of x and y values, I should be able to determine what the pattern is for this particular logarithmic function. So since I know it's a multiply-add, I look and I see here I multiplied by 2, and when I multiplied by 2, my y values increased by 3. So if I want to find 12, that's another multiply by 2, which means I should add 3 again, which would give me 13. And then if I multiply by 2 again, I'll end up with that 24, which means I should end up with, wait for it, that's right, 16. So let's just double check that. 13 and 16. Good. Alright, so now we want to find the particular equation algebraically using natural logarithms. Alright, so again, we take the same approach we took with all our other types of functions. We start with the general form, which is y equals a plus b, and here they're telling us to use natural logs, so ln of x. And I plug in the two given values from the first part of the problem. So y is going to be 7 when x is 3. And then y is going to be 10 when x is 6. Alright, so here we take it and we need to solve for a and b, and we have two equations with two unknowns. Once again, we have the choice of linear, or we have the choice of elimination or substitution. If I subtract, it looks like I could eliminate a quickly. So negative, if I subtract on both sides, negative 3 equals b natural log 3 minus b natural log 6. Alright, here I can factor out a b, so I have negative 3 equals b times the natural log of 3 minus the natural log of 6. I can apply my properties of logs and say that that is b times the natural log of 3 divided by 6. Subtraction results in a quotient. So negative 3 equals b times the natural log of 1/2, which tells me that b is negative 3 over the natural log of 1/2. So let's pull out our calculators here and figure out what b is equal to. So b was equal to negative 3 divided by the natural log of 1/2. Whoops. And that turns out to be 4.3281. So b is equal to 4.3281, and we're going to use that information to solve for a. So we'll take our first equation here, and we'll replace b with its value. So 7 equals a plus 4.3281 times the natural log of 3. So a is going to be equal to 7 minus 4.3281 times the natural log of 3. Once again, we call on our calculator. So we have 7 minus this value times the natural log of 3. And that turns out to be 2.245. So a is equal to 2.245. And if we're going to check that, let's see what we've got here. Yes, f of x is 2.245 plus 4.3280. Success. Alright, so let's recap. What is the general equation of a logarithmic function? Well, it's right here. Y equals a plus b log base c of x. What is the relationship between a logarithmic function and an exponential function? Well, we saw when we looked at the graphs and discussed them that the logarithmic function is the inverse of the exponential function. What are the key characteristics of a logarithmic graph? Well, if we look at those graphs, we can see that they're all increasing for x greater than 0. They're concave down. They all go through the point 1, 0. And then they will also go through the point of the base, 1. What is the numerical pattern associated with logarithmic functions? Well, we saw that the numerical pattern was multiply, add, which makes sense since the exponential function is add, multiply. And how do we solve for a particular logarithmic function given data or a graph? The same way we solved for all our other functions, by using the general equation and plugging in values for x and y to get a system of equations with the appropriate number of unknowns.